Welcome to the last session of the video series for the International Conference, Complexity Management, Leadership and Governance. In this last session, the subject is at the edge of chaos. So we'll be dealing with chaos theory. And the subtitle of the talk is Jurassic Park, Pandemics, Chaos Theory, and the Malcolm Effect. So we'll be looking at chaos theory, at complexity sciences, the place of chaos theory within the complexity sciences, as well as the Jurassic Park series, book series, and the film series, and their major implications in both culturally and for the main themes of the conference. So the conference is aimed at being a multidisciplinary reflection space on complexity, on management, leadership, and governance. And chaos theory and the complexity sciences are an important part of this reflection. And it's this point that we'll be seeing in this last talk. So my name is Carlos Pedro Gonçalves. I'm an associate professor at Lusophone University of Humanities and Technologies at the School of Economic Sciences and Organizations, and I'm a professor in the Department of Management on Civil Aviation and Airports. My research is focused on different fields, including complexity sciences, chaos theory, risk science, quantum technologies, artificial intelligence, strategic studies, studies in intelligence and security, fintech, and financial risk. I'm also a software developer in fields of complexity sciences, chaos theory, artificial intelligence, data science, and quantum technologies. And my major current research is focusing on empirical applications of chaos theory and the complexity sciences using topological data analysis and machine learning methods. One of the major points regarding chaos theory and the complexity sciences, which we'll be seeing, regards the probabilistic picture of randomness. So the main, a basic intuition on randomness that we had looking at randomness was that if it was based on a dichotomy between deterministic dynamics versus random dynamics. So if the dynamics was deterministic and the rule was simple, then the dynamics would only be regular. This was basic intuition. So basically, the dynamics would be either periodic or quasi-periodic. And the idea was that the effect would be of the same order as the cause, in a causality, applying a causality principle. And when randomness appears, when we find random patterns, then the tendency and the major approach to randomness would be to address it in terms of a probabilistic model, like a stochastic process. And we'll be seeing what a stochastic process is soon enough. So randomness, the idea was that randomness could only come from multiple independent factors, leading to unpredictable motion in large systems. So it became, when we saw randomness, it would be a large number problem, at least at the classical level. There's also quantum randomness, which is another issue. But examples of randomness, tossing a coin, Brownian motion, and the random walk are good examples of randomness. At the core of this, of our approaches to randomness, is the concept of stochasticity. And when we look at random patterns, for instance, and we have here an example of a game, looking at this game, and it's basically, it's one of the most basic games, and it's an example of a random walk. That is a walk on a line, where at each round, the player can walk either one step to the right or one step to the left. And one cannot take more than one step at each time. So these are the rules of the game. And at each step, we record the position of the player on the line. And looking at the position graph, we see here a few trends, but it shows a basically random pattern. And if we were to test for the independence of one step with respect to the previous step, we find that applying a test for independence, we'd find that the steps we could not reject inferentially, applying inferential statistics, the hypothesis that the next step taken by our player is independent of the previous step taken by the player. So, and if we look at the probability of stepping to the right, and the complementary of this probability would be stepping to, of this event would be stepping to the left. And if you look at, and we've seen this on the graph, on this second graph. So the first graph is a position graph. The second graph is the probability of stepping to the right. We see a convergence of the relative frequency to in a frequencist interpretation of probabilities. We see this convergence of the relative frequency to 0.5. So basically applying a test to this probability, to the frequency being to the true probability being 50%, we could not reject the null hypothesis of that probability of stepping to the right being 50%. For a significance level of 5 and 1%, we could not reject that hypothesis. So looking at random patterns and applying inferential statistics, looking at this random pattern, would be led to the following inference. Basically, the inference is that we are dealing with a stochastic process. That is a process where each step in this case is random, independent of the previous process. And so with looking at random patterns, and this holds for this game and holds in general when we look at random patterns, is that we apply the concept of stochastic process. So here, faced with this evidence, we'd be led to build a so-called stochastic process to address this random pattern. And what does this mean, a stochastic process? What is stochastic, and what's the relevance of this concept? So stochastic comes from the Greek stokos, with the sense of aiming, guessing, conjecturing. So we're dealing with conjectures. The trajectory of this term led it from the sense of conjectural work in the context of a probabilistic judgment in Bernoulli, to the sense of a probabilistic model. So a stochastic process was introduced within mathematics as formally introduced and defined in regards to a dynamical variable, so as a way to deal with randomness, where we have a dynamical variable for which the dynamics is not described by a deterministic rule. So we do not have a deterministic rule for that process, but instead we treat it as a random variable. So each value of the variable is drawn at random, from a specific distribution. And the idea, in the case of independence, we have each step, as we saw in the case of the walker, would be randomly drawn from a specific distribution. We'll be seeing the model, the stochastic model for that walker. It's called a random walk, a basic random walk. So the random variable has an associated probability space, and the future values of the variable are open. And at each moment, the value of the variable results from a random trial with a probability described by a probability distribution. So here we have the basic idea of what a stochastic model is. So we deal with the probabilist, we do not deal with deterministic rules. When faced with randomness, we calculate probabilities in order to deal with randomness, because the future values of the variable are basically unpredictable, but they can be predicted to a certain extent probabilistic. So we can calculate probabilities. And calculating probabilities using a frequencist approach, for instance, the relative frequencies converge to the true probability. That's the idea of the second graph. The relative frequencies converge to the true probability. And once we have that convergence and we see we have a probability distribution, inferentially so, we can calculate risk we can manage risk. And that's the idea of the stochastic model as a way to deal with randomness. In this case, we'd be led to conclude that the walker would be selecting at the game player, selecting at random each step. We'd introduce a Bernoulli random walk. Basically, this would correspond to a Bernoulli random walk. Bernoulli, why Bernoulli random walk? Because we're dealing with a binary distribution. At each step, the walker can either go to the left or go to the right. Each step in this case is independent of the previous step, and the probability that the agent moves to the right is equal to the probability that the agent moves to the left. That is a 50-50 probability. So this would be our model. And our assumption would be that the player is selecting at random, going to the left or going to the right. This would be our conclusion when faced with this empirical evidence. Our conclusion would be wrong, as we will now see. Basically, the game is being played deterministically by a simple rule. So, and this is where chaos comes in. So what's the game's algorithm? The next step is the next position for the player is equal to the previous position plus an S of t, which is the step. The step can either go, actually here is 1 minus 1, not 1, 0, 1 minus 1. The next step is either 1, if the variable is 0.5, go to the right, or minus 1, actually here is minus 1, if this variable, this underlying variable is at most of 0.5. And basically this variable, which determines the step going to the right or going to the left, you could also encode it as 0 and 1, as bit going to the right would be a 1, and if we draw a 0, we go to the left. But to add to the right as a positive direction and the left as a negative direction, we'd have to recode this 1 and 0 by 1 and minus 1. Okay, here. Basically, the going to the right or going to the left depends on the value of a variable. And this variable, which is z of t, it's our hidden variable here, actually depends on its previous value times 4 times 1 minus its previous value. And the variable assumes values between 0 and 1. So where does the randomness come in? The equations we do not see this randomness in the equations, looking at the equations. The equations are deterministic. The randomness comes from this last value. It can only come from one point, from one side, from the z of t. This means that this deterministic rule is somehow generating a random pattern, a random-like pattern. So, but the process is not probabilistic. It is perfectly deterministic. And there is an appearance of independence, of statistical independence, and actually you cannot reject the hypothesis of independence, but we are actually the steps of the player are being produced deterministically and with a strong dependence upon the initial conditions. A slight deviation in the initial conditions would lead to a completely different trajectory. The butterfly effect. So we have here a chaotic process, deterministic chaos. We'll be looking at precisely this equation for z of t further on and showing the chaos. So what we just saw as an example means that when we are faced with a random pattern, we may use a stochastic process to deal with it, but it may be produced by simple deterministic rule. So chaos introduces here a problem, which is it raises into question the dichotomy between stochastic and deterministic. And to assume this dichotomy thinking in terms of an ontological dichotomy with respect to systems is a mistake. So one must be careful in ontologizing the stochastic process in the sense of assuming that variable, which we assume to be random, and that variable's result at each time is ontologically non-deterministic. That is to say that its value is not produced by a deterministic process. So the stochastic process needs to be looked at as a tool to address a random sequence in order to allow us to calculate the probabilities when we are unable to find the dynamical rule or find the local conditions that may lead to the specific result. So assuming the adjective non-deterministic is problematic, second problem that is raised by chaos theory with regards to our own models to deal with randomness. And we need to consider here our cognitive limits. So when we assume that something, just because a dynamical pattern is random looking for us and well described by a stochastic process, for probability calculation purposes, that one cannot assume that such a process, such a dynamics, is actually the result that cannot result from a deterministic dynamics. So to assume that because the dynamical pattern is random and well described by a stochastic process, one cannot assume that it was not the result of a deterministic dynamics. This also means that to assume that because a process is deterministic, and this is the other side of the coin, to assume that because a process is deterministic, we cannot we cannot assume that we can fully predict it and control it. So it is a mistake to assume that because a process is deterministic, that we can fully predict it and control it. So it's the illusion of control that chaos raises. And this is a point, a major point. So faced with our own cognitive limits, it forces us to face our own cognitive limits. It forces science to look at problems, specific areas where it must, the simple fact that we are using a probabilistic approach because we are seeing a random process and that probabilistic approach works does not mean that we know everything about it. And sometimes what we assume to be random is actually the result of some underlying dynamics that we simply do not know or haven't been able to achieve in terms of understanding that system. And this is one of the major issues raised by chaos theory. So what deterministic chaos uh, um, forced us to look at is that it forces to recognize that simple rules can generate random patterns, that randomness can be endogenously generated by systems. So the source of risk is not necessarily external. Internal dynamics can lead to instabilities, can lead to unpredictable motion, and can lead to an internal source of risk. So the risk does, in economic terms, to look at bubbles and crashes as produced by external exogenous shocks, random shocks, is one of the points where chaos theory forces us to review in terms of an assumption. So we can have bubbles and crashes as a consequence of the system's own rules, a deterministic consequence. So determinism does not mean that a random pattern cannot be produced, a random looking pattern. So furthermore, limited knowledge of the state of the system leads to an inability to predict the system's dynamics after a few steps. And this is known since the end of the 19th century, beginning of the 20th century, by Henri Poincaré, by the famous mathematician Henri Poincaré, when he studied the three bodies problem. So this was that and the butterfly effect is already defined by Poincaré in his 1903 essay, where he states that small differences, it may happen in some systems that small differences in initial conditions can produce very great ones in the final phenomenon. So and a small error in the former, in our reading of the initial conditions, will produce an enormous error in the later, so that prediction becomes impossible, and we have the fortuitous phenomenon. Fortuitous from our standpoint, not from the standpoint, not all, it's not, we cannot assume that the system is not deterministic. So it's perfectly deterministic, the process, and the reason why the system went from A to B is completely determined by the initial conditions and the rules, the dynamical rules. Yet, from our point of view, we could not predict that motion, and that motion seems random to us, and this is chaos. So in the 1990s, the Jurassic Park books picked up this issue, and they introduced it from actually from a reflection on engineering, on biotechnology, on bioengineering. And the main issue, the main point of the Jurassic Park book, and to a certain level, the second book, The Lost World, and also the movies, especially the first, and now the Jurassic World movie, the last one, they lead to reflection on an engineering look, reductionist engineering and control look at biotechnology. So the idea that bioengineering and biotechnology that has a reductionist approach is capable of predicting the consequences of modifying organisms, of genetically modifying organisms, and can control the byproduct of that genetic modification. And that is the main issue regarding the Jurassic Park books, the problem of control, the problem of bioengineering, and the issue of whether one can control life. And the illusion of control is denounced in that the books are in the main argument of the book, and also in the movies. So strictly speaking, the book was not dealing actually with the de-extinction of the original dinosaur species. These were in fact new entities with a mixture of the original recovered DNA and gaps filled with bioengineering that included the hybridization of frog DNA. So the main point regarding the control of life, and this is the main point of that chaos theory raises, and Michael Crichton introduced in the book a character who defined himself as a chaotician, an expert in chaos theory and complexity research, which was Ian Malcolm, who was portrayed in the movies by Jeff Goldblum. And basically, that character served as a way for Michael Crichton to introduce the basic consequences of chaos theory and complexity sciences and what they mean for our perspectives on control, on a mechanicistic way of looking at systems, at complex systems, and on the idea that we can control complex systems. So the book addresses, therefore, the potential and risk, focusing on biotechnology. The book opens up this issue in a more general sense regarding what is a criticism to a reductionist and basically mechanicistic control stance, engineering control stance, which in the case of living systems is a problem because we have co-evolutionary processes, we have the interaction between genes and in the organism and the environment, the triple helix concept. And we have co-evolutionary processes that escape control. We can have unforeseen consequences of biotechnology, and that's the main issue raised in the book and in the first movie. We'll be looking at the last movie in a short while because it's very important regarding our present state as a society, as a species. So control and chaos. This is one of there's an interesting point because chaos theory forces us to recognize that some things, even when we have a deterministic rule for a system, we may not be able to predict the outcome. There are limits to our prediction, even knowing even if we know the rule. Um, but there is an area of mathematics that deals with chaos control. But there is chaos control. This is and we can apply it. We can apply it to specific mechanical systems. When we are dealing with complex systems, that control is rendered if that control fails. And the issue of control and in complex systems with chaotic dynamics is raised in particular by Konek and Suda. And this quote is particularly important regarding chaos and the consequence of chaos. And we need to take this lesson seriously in regards to our main point about management control and engineering and dealing with the problems that we are dealing now, like global warming, like ecosystemic unbalance, like pollution, accelerated extinction rates, which is what we are now facing. So we are facing a problem of planetary sustainability, and we need to take into account this. And the idea that we can control the consequences of our actions and that there's no problem, that we can always overcome even our biggest blunders, we can overcome them and solve those problems. Uh, this is not always so. And when dealing with living systems, we may fail as a species if we think like that. So chaos theory and complexity sciences force us to deal with that, to deal also with the failure of control and of a concept of control. And Kaneko and Suda, in this quote, raise that point specifically for chaos. We are not able to control chaos, even when we have the program for driving dynamical systems. When we have the dynamical rule, the algorithm, we are not able to control chaos by using that algorithm, and consequently, we are forced to use probability. And here probabilities enter into play. So there's this dialogue with stochastic analysis. In addition, chaos can generate information. And here we emphasize again, quoting now Kaneko and Suda, that if chaos is included in a system, more complex behaviors than those described in the program could in principle appear, especially in networked chaos, which was one of the major issues studied by Kaneko and his collaborators. So this school was very developed by Japanese authors. And they found that and this issue is a serious one because they deal with chaos in networks, so in complex nonlinear networks, which is one of the major points that globalization is leading to, complex nonlinearly co-evolutionary dynamics accelerated by digitalization and by the web, by the World Wide Web. So, so the necessary condition for emergence in the framework of dynamical systems occurs whenever we are dealing with chaos in complex systems. So, while chaos control literature is a subset of control theory, yes, the problem when dealing with natural systems with coevolutionary dynamics with emergent chaotic attractors is that the chaos, even when it is low dimensional, is not controllable. And any attempts at control will only add to the system's nonlinear adaptive responses. And these are either integrated in the system's dynamics in a way that reinforces that dynamics, or it can lead to qualitative topological changes in the system's dynamics, leading to possible bifurcations or dimensionality changes, which resents to a change in the emergent attractor's structure. And this is the major issue regarding control. So in open coevolutionary contexts, as the number of when we have number of elements in interacting systems that can change, emergent attractors need to be looked at as emergent geometries associated with these systems' collective dynamics. And the dimensionality of these geometries can also vary with time, which means that unpredictable structural changes in the dynamics can lead not only to topological changes with a conserved dimensionality, but there can also be changes in the dynamics leading to different emergent dimensionality. That is, the collective dynamics changes in the number of emergent active dimensions, which would lead to a breakdown in ex ante equations. So if we write equations assuming that a number of variables are determining this system's dynamics, a number of macroscopic variables are the key variables for understanding the system. But if the dimensionality changes, then we have unaccounted for variables and we have a structural change, and our equations are rendered null. So dimensional changes lead to problems when the equations are used for control, since the optimization solutions and even the dynamical rules can change. And this is one of the points. So the idea that we can control life was the main, which was the main point and as a criticism to a reductionist molecular biology standpoint, supporting a biotechnological effort, a biotechnological effort informed by a bioengineering thinking, is majorly criticized in the first book in a basic quote that the history of evolution is that life escapes all barriers. So that idea that we can control life is a problem. Life breaks free. Life expands to new territories, painfully, perhaps even dangerously, but life finds a way. This quote, which was also used in the movie in the Ian Malcolm's speech, was is one of the basic messages of the first Jurassic Park, and this also leads to questions regarding our attempts at dealing with problems like global warming, like financial crisis, accelerated extinction rates that we are seeing now, and ecosystemic degradation. So our life support system, our planetary life support system, is being placed in question by our own behavior, by our own actions, and this is a problem. We are we and this is not a long-term problem. And this is a problem because if we think that we can overcome it with solutions, there may be a point beyond which we cannot, our solutions all fail. And we either collapse as a civilization in terms of into a Mad Max dynamics, and it's very easy for that breakdown to occur if we think those types of situations can occur very rapidly. It's called a phase transition in complexity sciences. But we can also have our collapse as a biological species. So other species have gone extinct. And that is actually the main subject of the second book, and we'll be seeing that issue in a short while. So there's an interesting point regarding the Jurassic Park catastrophe that I've seen made in a few analysis of the book and the movie. Actually, in the movie, they have a problem. In the movie, you can make that argument more or less, not very much because the dinosaurs were reproducing. But in the main argument is that the park only failed because there was a disgruntled employee that led to the failure of the park, and that was what escaped control. Insider threat management. This is a major issue. Insider threat in management, and moral hazard. But and it's a human resources management problem, and that is very well expressed in both the movie and the book. But the problem here is that in the book the park was already failing. Why? Because the surveillance and control, because of an assumption, the engineering systems assumed that the dinosaurs were bioengineered as all females, so they could not reproduce. The problem was that by hybridizing which was an engineering solution, by hybridizing with frog DNA, they were able to change sex and reproduce. And this happens in the book. They are reproduced and in the movie. But in the book, the issue is raised regarding the control. So the park was already failing independently of that disgruntled employee. Why? The animals, the counting process for animals assumed that the number of animals released counted with the user introduced the number of animals to be counted because they were afraid that they might lose animals. So the issue was keeping the animals contained. The problem was that the animals were already escaping, but because they were reproducing, they had more animals than they had released in the wild. And the system counted the animals, and when it reached the number of expected animals, the system stopped counting. And they discover that and it's Ian Malcolm who discovers this, and he discovers that if they introduce more in that threshold, that counting limit was raised, actually they had more animals than they had bioengineers. And so they discovered that the animals were reproducing. Not only were they reproducing, but they were escaping the island, and raptors were already on a supply ship. And this is in the book. So the park was already failing. Life was already escaping containment, both in terms of reproduction, escaping the bioengineering plan, but also escaping the containment of the island. Um, so and this is the issue. The disgruntled employee line. This is not actually work that is worked only in regards to their reproduction, but not escaping the island issue in the movie. But the disgruntled employee side is worked. The insider threat is worked in both in the movie and also in the book. So, but again, the issue is one of the control of the failure of control in regards and unpredictable behavior, in this case regarding human behavior and both the animal behavior. And this is worked in the book with various cycles where they have an illusion that they regain control, that the crisis was solved, but then a new crisis occurs, and the park at the end breaks down. And this is one of the major issues, and it's a reflexive issue. It's an adaptive issue. We assume that we have good theories of how the world works, and that and in a reductionist mechanicistic standpoint, market oriented in that view of life. If you look at life at living organisms as machines, and we think that we can predict the consequences of our actions and manipulations of those organisms. And if we think that we can always find solutions for living ecosystems, for instance, we may be heading for a failure. And the failure is one of the models themselves. So the models offer a pale view of reality, and the idea and the reductionist approach leads to narrow solutions, directed solutions, but there's a whole host of consequences that cannot be anticipated. This holds for genetic manipulation. We can alter genes and think that we have solved a specific problem, but the issue of a link, a mechanicistic link, does not hold here, and unintended consequences can come. And this is the major issue of the first book. And the first book leads to the issue of the reflexive failure, and the second book picks up this. So the possibility that complex adaptive systems, which include human societies, can fail to solve problems while they were but supposedly they should be able to deal with those problems, but they still fail and they still collapse. And that issue was actually discussed in the Santa Fe Institute. The collapse of traditional societies has been researched and not only which Santa Fe Institute, which was one of the institutes that addresses complexity sciences, but it has also been addressed in particular by Jared Diamond in the book Collapse. And that book shows how different societies, how human societies have collapsed, and adaptive failures of human societies. And that's essentially a reflexive failure. And this is picked up in the second book, The Lost World, the issue of extinction. And we are seeing the accelerated extinction rates. We are seeing this and this is a problem. We are seeing ecosystemic degradation, and these are irreversible consequences. There are irreversible consequences associated with this. So, and our human and the human action, the so-called Anthropocene, which characterizes our era, where human action affects the geophysical and biological systems, is one of the major issues that is threatening the sustainability of our species. So, and this issue is actually raised in the second book, which is the possibility that complex species can become extinct, not exactly because of a change in their physical adaptation to their environment, so phenotypical change, but because of their, in terms of physiognomy of the species, but because of a change in their behavior, which also has a phenotypical dimension. So, but the basic idea is that complex animals could possibly go extinct because of animal species could go extinct because of a failure to adapt. And this is where the second book goes, the direction where the second book goes, the possibility that complex systems, and the second book works on a concept that we'll be seeing shortly, which is the so-called edge of chaos. So, and the book actually picks up on this concept, which comes from complexity sciences. Actually, it does not come exactly from chaos theory, it comes from cellular automata theory, which is a branch of artificial life, which is one of the models of artificial life, computer models that simulate automata and simulate artificial ecosystems and so on, and coevolutionary systems using computers. So coevolutionary computation, basically within automata theory in the case of cellular automata. And basically, the concept of edge of chaos was worked there, and as well as in random Boolean networks for within evolutionary biology by Stuart Kaufman in the case of random Boolean networks. And the concept of edge of chaos was worked in that context, not exactly in the context of chaos theory, but we'll see that it applies as well to chaos theory. And this is one of the major subjects of the present of this presentation. So the edge of chaos, and is very well defined in the book. It's looked at as a place where there is enough innovation to keep a living system vibrant and enough stability to keep it from collapsing into anarchy. This applies to companies, this applies to markets, applies to human societies, applies to biological organisms, so and species in ecosystems and so on. So the idea of the edge of chaos is that it is a zone of conflict and upheaval where the old and the new are constantly at war, and finding a balance point must be a delicate matter. If a living system drifts too close to the edge, it risks falling over into incoherence and dissolution, so into the chaotic side. But if the system moves too far away from the edge, it becomes rigid, frozen, totalitarian, and is unable to adapt. So both conditions lead to extinction, and too much change is destructive, as destructive as too little change. And only at the edge of chaos can complex systems flourish. And one of the assumptions sometimes made within complexity sciences one of the conjectures actually made in the complexity sciences was the possibility that complex systems might co-evolve towards the edge of chaos and stay there. The problem is that that is raised in this book by Michael Crichton, and it's a very important and very interesting issue for complexity sciences because it actually can be raised, and we'll be seeing that in the case of COVID-19. Um, the issue is the possibility that a system that may co-evolve towards the edge of chaos, the co-evolutionary dynamics towards the edge of chaos, may not stay there exactly, but it may changes, qualitative changes in the dynamics can occur either to one side or to the other, actually, as just like Michael Crichton raised in the book. So it may be unstable, that edge of chaos. The coevolution towards the edge of chaos may not be as stable as an early conjecture might assume. And that conjecture actually ends up being born out of an idea that a positive or optimistic idea that complex systems could actually optimize, and which resends again to an idea of control, that we as our societies could optimize at the edge of chaos and survive and be vibrant, and never drifting either to an anarchy or to a rigid system that is unable to adapt to a changing environment and that collapses as a consequence of that. So the issue is that that edge of chaos is not as stable as one might think. So bio in the Jurassic World Dominion is very interesting because it leads to the other level of this problem of the adaptive failure. Our adaptive failure, it raises the problem of our current adaptive failure, our danger. We are at danger as a species. And we are at danger as a species because of one consequence of our current state of affairs. We are living from one crisis to another. We have wars that destabilize economies, that lead to inflationary pressures. But we just stepped out of a pandemics, and early on we had and we had crises like the subprime crisis, then the public debt crisis in Europe. And so we have this shortening of cycles between crises, and we seem to be dealing with the crisis has become the permanent in our societies, and this goes from both the economic side, the, the warfare between states side, also the geopolitical side as well. But we also have this problem of the crisis associated with the ecosystemic crisis, the global warming, climate change, and so on. And this is a problem for our species because we are going from crisis to crisis and dealing with multiple crises at the same time. But then we are adapting to this situation, and our economies seem to be taking advantage of this. And this is this leads to the issue of the crisis capitalism, which is well addressed by Naomi Klein in the Shock Doctrine. Okay, but it's also a major issue because we are beginning to get used to living with crisis one after another, and profit from crisis even, and this leads to the crisis capitalism, and the illusion of control in the case of the Jurassic World Dominion, is coupled to this, and the biotechnology danger is coupled to this problem. In this case, biosyn bioengineers launch a plague of locusts, create a global crisis in crops in order to corner the world market and sell their biomodified seeds, as they lead to the only crops that the locusts do not attack. The problem is that they lose control over the locusts, and this crisis could lead to global collapse. So the Jurassic World Dominion takes the problem to a new level, beyond the books. The books were we had this containment in islands and the escaping the containment from islands, but the world at large was not as at stake. That issue of the world at large being at stake was not as developed in the books and in the first movie franchise than in the second. In the second, with the last movie, the issue of the crisis capitalism, the issue of even the engineering of crisis to profit from the crisis, is raised. And this is the problem raised in the movie. And the issue is not no longer one of losing control over a park, is about the illusion of dominion over nature and control over the planet, which makes the title of the movie very well chosen, the dominion, the illusion of dominion. And it raises the problem that we might collapse due to our inability to deal with the consequences of our actions stemming from a mixture of illusion of control and greed. So both the second book and the Jurassic Park Dominion raise a similar problem. And while the argument raised in the second book is also raised by Jared Diamond's collapse of different societies over history, the movie takes that argument to a new level and it introduces crisis capitalism as a possible source of collapse. So the market opportunities raised by crisis may lead to market interest in crisis and to possible adaptive failures of the human species, ultimately leading to its collapse. And this is one of the major problems of crisis capitalism. Um, uh, this quote from Maria Odete Madeira, my mother, with whom I collaborate. My mother is a philosophy researcher, ontology, systems philosophy, and so on. And my mother reflected on this issue. And this quote is specifically important in our main argument. So, crisis is the generalized, threatening, referent, and reference that pulverizes the daily cognitive dynamics of the now human present, which is what was the argument that we just saw, with a permanent alert that it is the case that we are in the imminence of collapsing as a species, and that not even the crisis market as resource and opportunity to an unwise, opportunistic, desperate maintenance of the current structures of economic, political, military, and social power is able to erase the evidence that is there for all to see. We have arrived, as other species before us, at an evolutionary dead end which appears to menace us with the status of failed species. So it's our collapse as a species that we are facing. And the inability to see that is a problem. But the illusion of dominion is a major issue. And that illusion of dominion, in a sense, follows well a religious, what has been a basic religious picture that is strongly present in a Judeo-Christian mindset, that God created us at His image and created the world for our benefit. So we are the pinnacle of creation. We are not, uh, and, uh, and and to bring that mindset, to bring that cultural picture to evolutionary dynamics, and to think about an evolutionary ladder where we would be at the pinnacle is a problem. And the issue of crisis capitalism um, is one of the major issues that resents to the possibility of an adaptive failure because we are feeding from the crisis themselves. Then we are investing in the end up investing in the crisis. We end up there are in the human co-evolution, social, economic, political co-evolutionary dynamics. There is a side that ends up uh, uh, seeing a winning situation by from the crisis, from crisis, taking advantage of crisis. Crisis becomes an opportunity, but the crisis end up being increasingly disruptive. And in the end, we are banking on our own extinction. So betting on, we are taking advantage of the extinction process. It's more like moving towards a precipice and charging money for jumping. So, and the more people want to jump from that precipice because they can win $1 million. That $1 million does not serve anything because they still, you can be a billionaire but still fall from the precipice, and the $1 billion go down the drain. So you're not there to enjoy, at least. So that's the issue, the main issue, and the crisis becoming an object of desire, becoming a commodity, a product, dra dragging the seduced agent. This issue leads to the problem that we end up living for the crisis and feeding ourselves from the crisis because that's all we have, and it's all that that is left of ourselves in ourselves. So this issue is, quoting again from Maria de Madeira, this issue is the main problem of crisis capitalism, which is also raised both in this article from Maria de Madeira and in another article that raises the point that the crisis is us. So we need to change ourselves in order to solve the problem. So the issue here is sorry. Um, the issue here is one of changing. The change needs to start in us as a species. So the change must occur in us by synchronized, globalized self-determination. Um, in this case, two ends of survival and dignity, the survival of each and every one, because we depend on each other. We are entangled with each other, and the inalienable and irreducible dignity of each and everyone is important, is it's a critical point regarding because of survival and sustainability. If we fail, if we fail, we all fail, and that's the main issue. And this is also raised in the movie regarding the the change that needs to be undertaken. And again, the Ian Malcolm character picks up on that in the movie. So this is not any quote from a book. It was written for the last movie itself. So the reflexive failure is a problem, is an issue. Adaptive failures are an issue that needs to be studied within complexity research. And here the issue of the possibility of blocking of homeostatic mechanisms and the problem of the neurocognition of risk needs to be raised here. And this is the main issue regarding it's a reflexivity problem. The issue raised in Michael Crichton's second book, so The Lost World, is very was very is very well placed because it raises the possibility of adaptive failure of complex systems, of complex adaptive systems, and that's an issue that we need to take into account, and it's an issue that complexity sciences need to look at. So there are two main questions that we'll be seeing from now on in this lecture. So Ian Malcolm was actually hired in the first book to analyze the Jurassic Park, and he predicted that the park would fail because of the behavior of the system in phase space. So the basic issue is then, what is chaos theory? And is it possible to do what Malcolm did for Jurassic Park in terms of analysis outside the fictional world of Jurassic Park? I'll be showing you that it's not only possible, but I'll be showing you how to do that and examples of this very point. But to do that, we need to look at chaos theory, the concept of chaos theory first, and the role of chaos theory within the complexity sciences, within complexity research. So chaos theory, basically deterministic chaos. There are different definitions, but this is a good one. It synthesizes well the concept of chaos. Deterministic chaos corresponds to bounded non-periodic dynamics with sensitive dependence upon initial conditions. So bounded, it means that the dynamics is fluctuates in a certain region of values. It has sensitive dependence on initial conditions. It means that a small change in the state of a variable it will be amplified over time and lead to a different dynamics, which is the main factor of unpredictability in chaos, and is called the butterfly effect. The flapping of the butterfly wings changes the weather somewhere around the world, produces a hurricane in another place. So that's a metaphor, but basically the idea is that we can there is an amplification of the smallest fluctuation will be amplified and will lead to great changes, and there's a limit to predictability. And random looking trajectories, despite the dynamics being deterministic. This is the other side of chaos. There's also another type of deterministic chaos. Chaos theory also deals with the so-called stochastic chaos. What is stochastic chaos? Basically, it's an open chaos dynamics, corresponds to dynamics that is affected by external factors that can be mathematically modeled as external noise. And there's an endogenous chaotic dynamics. So in this way, even in the absence of external noise, the system would still exhibit random looking dynamics, and small fluctuations in the environment will be amplified and lead to diverging dynamics. So and there's a fundamental unpredictability that carries over to this context of stochastic chaos. So this is an example of chaos. Um, and this is actually the author that coined the term butterfly effect. And we have here a model that he introduced, Edward Lawrence. So there are three variables, and basically their equations for the velocity for each variable. The equation for the velocity of each variable is up there, and basically the velocity for x depends on y and x, on the value of y and x at that time. So the velocity depends on the position, and there's feedback between these different variables because the velocity for x depends on y and negatively on x. But the velocity for y also depends on y and on the position for the y coordinate, but also depends on x and on z. And basically, the velocity for z also depends on a nonlinear product here, or on the product on a nonlinear terms here, the product between x and y, but also negatively depends on z. So there's feedback between the different variables here. Each variable a negative feedback of x on x, positive for influence of y on x, and so on. So you can analyze this in terms of a system of relations within system dynamics. And basically, we have three variables. And if you look at the trajectories of the variables, they look random. Small fluctuations in the initial conditions would lead to completely different trajectories over time. But there's an order here. And if you look at this, the trajectories of the different variables and picture them on a three-dimensional space for the three variables. And here we have the position of the system at each moment, at the different moment of time. The dynamics is in a bounded region of the space of the different dynamical variables, the so-called state space or phase space, which is basically described by 3 degrees of freedom, a three-dimensional space. And the trajectory lives under commas in this lives in this three-dimensional space, but it is a, a fractal structure, and this is the so-called strange chaotic attractor. So any 2 points, the trajectories all live within this space. Two trajectories starting near each other will diverge and visit different regions of the attractor at different times, but the trajectories are attracted towards it. And we have here a chaotic dynamics, a chaotic attractor. The structure of this attractor is actually, and here we reach one point that it's that chaos is another level of order, is a more complex order in complex in systems. So what appears to be random actually has a new type of order in the dynamics that can be captured by these geometries. So it has this fractal geometry that is a proper of the system. The fractal dimension, the divergence rate between the different trajectories, which is the largest Lyapunov exponent, which characterizes how small error is amplified over time. All that characterizes the system is a structural point that characterizes structurally the dynamics, and the attractor itself, the structure, the topological structuring of the attractor is a key in looking at the system, in analyzing the system, and even at attempts of prediction. Chaos can be predicted within limits, and this is one major point that can be used actually for management. And we'll be seeing that not exactly for a control of the system, but for adapting to that problem. And we'll be seeing that about SARS-CoV-2 and COVID-19. So chaos theory forces us to distinguish, as we said, between the risk associated with external random shocks that disrupt a system from without, and the risk endogenously generated by the system's own nonlinear dynamics. And when dealing with complex systems which are open and interact nonlinearly with an environment, we never have a fully closed deterministic process. So noise is always, in terms of a closed process with a few number of equations, not, so-called noise is always present. There are many degrees of freedom, so there are new agents coming in, coming out, going out. So there are fluctuations in the number of what would be the variables in a microscopic dynamics. But emergent attractors can occur, and these emergent attractors can occur and be sustained by that micro level dynamics. And this is a point that we'll be seeing soon enough regarding chaos in complex systems. Chaotic attractor emergence is one of the main points when looking at actual empirical examples of chaos in nature. Not talking about the chaos in mathematical models where you have those equation sets. I'm talking about the chaos occurring in complex systems, and being able to identify those markers of chaos and reconstruct the attractors, which is one of my major research lines, current research lines, and I've done that worked on that in particular in epidemiological contexts in the case of SARS-CoV-2 and COVID-19. So systems can exhibit emergent dynamics with specific geometric and topological properties that can be addressed in a finite dimensional geometric space characterized by a chaotic attractor. It was this type of analysis that Ian Malcolm supposedly did for Jurassic Park and allowed him to see that there was something identified from the early start in a qualitative interpretation of the attractor's dynamics, allowed him to find that there was something wrong with the park. Of course, this was a narrative device from Michael Crichton, but it's possible to do that, and we'll be doing that precisely for COVID-19 soon enough. We are not out of the pandemics yet, and we know that we are not out of the pandemics. We are the COVID-19 is continuing. New variants are surfacing, and they are causing problems here in Portugal. That which is where I live, and which is from where I'm talking to you, in Lisbon. Here in Portugal we are having a problem with COVID-19, and we'll be revising reviewing that issue, and where we stand regarding that virus. So there are the main dynamics that we can categorize. We have cyclical or periodic dynamics. These are fixed point, for instance, which is a period one cycle, steady state, higher period cycles, quasi-periodic dynamics, and random dynamics. So random dynamics, we now know that they can result from deterministic dynamics, cellular automata theory, deals with that. Chaos theory deals with that. Endogenous randomness. Randomness that we also have random dynamics that can occur from an accumulation of different factors leading to a statistical noise, which is dealt with strongly with stochastic process theory, and statistical mechanics also addresses that and why that is so. Uh, this is in very, very, very large systems, for instance, in gases, you can work with that, resulting from an intermixture of endogenous randomness and statistical noise, which is dealt with, for instance, in case of chaos theory, in stochastic chaos, in the specific line of stochastic chaos. Then we have the edge of chaos, which is the main subject of this talk, where we have an intermixing of periodic, quasi-periodic, and chaotic elements. And it can occur in cellular automata. It can occur in coupled chaotic dynamics, and in the case of chaotic systems, at the so-called onset of chaos, markers of what is called the edge of chaos, that we already saw a good definition by Michael Crichton, are examples of the edge of chaos. So while the edge of chaos was initially proposed within cellular automata theory, and within those type of random Boolean networks. It also occurs in chaos, in both low dimensional chaos and networked chaos. And it at the onset, so-called onset of chaos, which is near a point between a periodic dynamics and a chaotic dynamics, so-called bifurcation point for chaos. Near that point, we get edge of chaos like markers. We'll be seeing what are these edge of chaos like markers in a short while. So what does the chaos research involve? Study of bifurcations and catastrophes, study of transitions from periodic or quasi-periodic dynamics to chaotic dynamics, study of chaotic attractors and markers of chaos in different systems, ranging from physics to biology, computer science, social sciences, and so on, modeling of turbulence and complexity research, networks of chaotic oscillators, for instance, and it's strongly linked as well to computer science with a link between algorithmic randomness and chaos. So chaos has strongly influenced complexity research, and we've been talking about complexity since the beginning and throughout this conference. And it's the major subject of this conference, and it's important to consider what complexity research involves. So basically, when we deal with complexity, we deal with systems with many parts and interacting parts, often non-linearly interacting parts, where emergent dynamics occur. It's a problem of the complexity is an issue, is a matter of number and geometry. And basically, the complexity research, um, actually, there was a certain confusion at the beginning of complexity research, and people sometimes called it complexity theory. Actually, there are different theories within complexity research, so there is not one complexity theory. There's algorithmic complexity theory, there's complex adaptive systems theory. There are different theories. Chaos theory is also a part of complexity research, has become a part of complexity research. So we have different theories working here. We also have different sciences working here. So we can talk about complexity sciences, or basically a complexity research platform. Perhaps the term platform would be the best term to characterize complexity research. It's an interdisciplinary research field organized like a research platform that takes complexity as its object of research, where different sciences that deal with complexity in their respective fields dialogue with each other and try to develop a common arguments, a common dialogue, and fertilize each other's models and theories. So it has, although it's an open platform with this diversity of fields that go from the human sciences to physics. It also has core paradigmatic elements that come from cybernetics, from the cybernetics paradigmatic basis, that evolved from the initial cybernetics, which was focused on control, but then introduced the concept of feedback, yeah, the biocomputing, and so on. And cybernetics also the cybernetics philosophical basis interacted significantly and converged significantly and intersected significantly with structuralism, and basically we have here the cybernetics basis strongly influencing complexity research. It's one of the core paradigmatic elements that comes from complexity research. Then we have computer science, including computational complexity, automata theory, genetic algorithms, and agent-based simulation. Machine learning and artificial intelligence also strongly developed within one of the major institutes that address complexity, which is the Santa Fe Institute. The concepts of edge of chaos, complex adaptive systems, self-organized criticality were all developed by the Santa Fe Institute within the context of the Santa Fe Institute research. Then we have system science and philosophy. It's also a major core paradigmatic element in complexity thinking, with core research and influence developed by two schools of complexity mainly, which is the Brussels Austin School with Ilya Prigogine, who introduced the dissipative structures and both classical and quantum chaos, and the Stuttgart School with Hermann Haken synergetics, which is particularly important in terms of its implications on complexity thinking. These two schools, Ilya Prigogine and Hermann Haken, were the first major schools of thought and of research within complexity. Santa Fe came a little bit later. And Ilya Prigogine basically was a Nobel Prize won the Nobel Prize in Chemistry in 1970. So for the introduction of the concept of a dissipative structure and empirical work on the subject, and the concept of dissipative structure addresses already the concepts of major concepts of complexity, which is self-organization, far from the thermodynamic equilibrium, the possibility of spontaneous self-organization processes by virtue of exchanges with the external environment, the emergence of ordered structures in what seems to be a random, or what would be initially a random pattern, but that order can emerge from randomness. Long range correlations, all these problems are addressed, and the ability of open systems to operate far from the thermodynamic equilibrium is a major issue. Hermann Haken, in turn, had pioneering work in laser physics, quantum field theory, far from equilibrium systems in the thermodynamic sense as well. And his conceptual research focused on self-organization, emergence, and the synergetic dynamics of complex systems. So synergetics here deals with cooperation, synchronization, cooperation, symbiosis, and provided the foundational synthesis for a major foundational synthesis for complexity research, and is a very important, has a very important framework to deal with, and very effective framework to deal with complexity. So the term synergetics was borrowed from the concept of synergy in the sense of cooperation, so in the sense of working together. So from the Greek root and the philosophical root. And the synergetics, the major differences, Prigogine worked in Brussels, in the Brussels School, and then in Austin, Texas. So he led to the so-called Brussels Austin School for Complexity, and the Hermann Haken's group, the Stuttgart School. So Brussels Austin came out mainly of the work developed in the 1950s and the 1970s, up to the 1970s, with strong foundational work on dissipative structures and far from equilibrium systems, expanding to interdisciplinary research in complex systems, with chaos theory playing a major role in the Brussels Austin School. In the Stuttgart School, 1960s to 1970 and 1970s, 1980s, and so on, came synergetics. And while Prigogine's school looks at complex systems in different contexts through the lens of thermodynamics, open systems thermodynamics, and statistical mechanics of open systems operating far from equilibrium. Aken's work, while also working with this, is more based on general systems philosophy and focuses on systems considered for themselves and not specifically working from a thermodynamics lens, which does not mean that statistical mechanics and thermodynamics are not also addressed within the within Aken's work. But basically, the main issue is that Prigoghine's school was strongly influenced by the concept of dissipative structure and the thermodynamic framework, while the synergetic school was strongly influenced by the concept of the working together, the synergy, the cooperation between many elements and self-organization linked to that concept of synergetics. So synergetics was based on a conjecture that system science and philosophy can be effectively developed in that there are generalizable elements and processes in common to different systems that are amenable to scientific research and that complexity can be approached working from concepts linked to the cooperation between systems parts so that emergent dynamics and self-organization can occur within these contexts. And it's an attempt to explain self-organization and emergent dynamics from this standpoint. So, and this basic conjecture is the first well-structured, uh, um, uh, uh, more mature thinking, basic conjectural route for complexity research in general. That is the conjecture that complexity that there are common elements in different systems and that complexity can be approached scientifically in different disciplinary fields and using an interdisciplinary dialogue. And this is the major issue of synergetics. So synergetics can be argued to be the first major attempt at a full-blown integrated research on complexity. And basically, this idea is that it focuses its attention on spontaneous, dynamic, self-organized emergence of new qualities, which may be structures, processes, or functions. Basic question dealt with by synergetics is then, are there general principles of self-organization irrespective of the nature of the individual parts of the system? And this point is the one that offers the basis for a foundational thinking on complexity. So the major issue is that in spite of the great variety of individual parts, which may be atoms, molecules, neurons, nerve cells, up to individuals in a society, this question, this basic question can be answered positively for a large class of systems, provided that attention is focused on the qualitative changes on macroscopic scales. And macroscopic scales mean spatial and temporal scales that are large compared to those of the elements. And the working together, that synergetic process, may take place between the parts of a system, between systems, or even between the scientific disciplines themselves that are addressing complexity. And this is the major point of synergetics, which is that second sense of being a platform for dialogue between different disciplines. That complexity demands an interdisciplinary approach. So it's not as focused on the thermodynamic side and the statistical mechanics side necessarily, although it applies the methods from statistical mechanics and thermodynamics. It's the issue is that its focus is rooted in interdisciplinary. And basically, the idea of synergetics opened up the issue, the field of complexity, dealing with physics, chemistry, biology, medicine, cognitive science, computers, psychology, sociology, economy, ecology, philosophy, epistemology, control theory, electrical network theory, language theory, information theory, management theory, neuroscience. All these elements were addressed within synergetics. This actually opened up the issue is it opens up as a movement, opened up the way for other institutes to surface. And the third major institute to surface addressing complexity was the Santa Fe Institute, which is strongly born out of the Los Alamos research, uh, Los Alamos National Lab, and founded in 1984. So it's younger than the other two schools. While in the case of Brussels Austin, it's very focused on Prigogine's work, and the synergetics was strongly influenced by Herman Aachen, and Aachen is the major figure. There is no central lead person in the Santa Fe Institute. At its root, it was more aimed at providing for an open reflection and discussion platform on complexity, so it's more paradigm free. Even though it has a largely open approach on complexity, there are a few elements in the Santa Fe Institute that came out of a few pillar elements that characterized Santa Fe Institute, which is the artificial life approach. What does artificial life means? Means computer simulation of artificial systems, of artificial biological systems. Simulation of an ecology, simulation of co-evolutionary systems, and so on. And so this led to both cellular automata research, which actually has origin in von Neumann's work, genetic algorithms, the other side of here, which was introduced. Genetic algorithms were introduced by John Holland, who worked from a cybernetics standpoint. Artificial life, and then agent-based simulations, so multi-agent simulations using artificial intelligence, strongly influenced its approach, its major research tool works. So key areas such as self-organization towards the edge of chaos was a major concept introduced within the Santa Fe Institute in cellular automata theory and random Boolean networks, and self-organized criticality theory, which we'll be seeing in a short while, were products of this institute's research. Basically, what we have here as well in complexity research, when we look at complexity research, there are also a few models that come from statistical mechanics. And there are two major issues, two major models that are very important. The guess model basically deals with guess-like dynamics. So the agents interact and move in the screen and interact with each other. The field model, actually, or field or models that deal with fields properly, are very important in complexity research. All of the network models, like cellular automata, coupled nonlinear maps, chaotic networks, and so on, can be addressed as fields on a network. So we need to go beyond the mathematics and the physics in the case of the fields, and look at the ontological level of fields as well. So the field model has much yet to offer in terms of thinking. And here we need systems philosophy. So a field-based approach demands also a questioning and a fundamental reflection from a systemic and ontological standpoint. And in this case, we are dealing with systems philosophy, and we need systems philosophy within complexity research to expand on this last point, the field model. So let's look at chaos now. Here we have basically a chaotic map. And it's the same map that was responsible for that random walk that we talked about in the beginning of this presentation. And basically what we have here is that the next state is equal to b times the previous state times 1 minus the previous state. For b equals 4, with x being between 0 and 1, whatever the initial condition where you start, the dynamics will show this random pattern. It's non-periodic, it's bounded to the interval between 0 and 1, and starting with points very close to each other, they will diverge over time. Basically, we have here the so-called bifurcation diagram for this map, and it shows the dynamics for different values of the parameter. In this, for these values of the parameter, we have fixed point. When we have this, then we have this bifurcation. where the dynamics jumps between is oscillating between two points, and this is a cycle, a period two cycle. Then we have period four cycle, and so on until we have these regions of fluctuations. These regions of fluctuations correspond to these field regions of dots, actually correspond to these when we place the parameter to b to these values, we have basically chaos. So these are the chaos regions. And within the chaos regions, there are these regions that seem to be these white regions. Actually, they are periodic windows. That within the chaos, if you for the parameter there is another bifurcation, and we have you can transition from chaos to a periodic dynamics. And then what is a bifurcation, basically? Actually, the name ends up coming from these formations of these fork-like structures, but basically the concept is that of a qualitative change in the system's dynamics by when a control parameter changes. When a dynamical parameter changes, for instance, this growth rate, this was applied in this case this nonlinear map, which is called the logistic map, used for logistic growth actually, was applied to was a map used in population growth, so biological population growth. So the B here is the growth rate. When there are limits to growth for specific values of the parameter, chaos can occur. Here you see the butterfly effect. Basically, a small deviation in initial conditions, and we have a very small deviation, 0.0001. Initially, the two trajectories are close to each other, but after a while, they diverge from each other, and we have the butterfly effect. And here we have an example of one of the values of the parameter for 3.555. Here is for the value of the parameter equals to 4, but for 3.555, we have a periodic dynamics, and here we have a period 8 cycle. If we apply spectral analysis to this, we find here spectral spikes. These spectral spikes basically characterize periodic characterize cycles. So whenever you have these spikes, this means that there is an added energy here associated with these cycles. So we have cycles here, a cyclic behavior. For chaos, we have the spectral analysis leads to this type of spectrum, of power spectrum. And basically you can connect the dots or leave the dots unconnected in the time series chart, and you have here you see here the random like fluctuations. If you do spectral analysis, you get you do not get these regular spikes, you get this noisy like structure, which being flat corresponds to what is called white noise. So basically, this is the power spectrum for this nonlinear dynamical system, which is perfectly deterministic for B equals 4. But now when we are near the edge of chaos, or we have here the concept of edge of chaos working in a network of coupled chaotic maps, which replicates, which corresponds actually, which matches well also the cellular automata concept of edge of chaos. And the concept in the case of network of systems, we have these localized regions that propagate, and then we have intermittent turbulence points here where there is these branches meet and there's turbulence, and then they diverge again. So you have a mixture of regular dynamics followed by what seem to be random-like dynamics propagating throughout the series. So the oscillators are in each row. We have the chaotic oscillators, coupled chaotic oscillators. This is a coupled chaos network, and basically each row corresponds to a different moment of time, and we have I think 100 oscillators here, and we see the different steps of the system. Okay, So this is the edge of chaos that was worked in was early on identified in cellular automata random Boolean networks, and that also occurs in coupled nonlinear dynamics, coupled chaotic networks. It also occurs in the case of a simple map like this one, a simple chaotic system with just one dynamical variable, 1 degree of freedom. And here it occurs, we can see this pattern, the pattern of the edge of chaos here, well characterized. For b equals 3.58, we are near a bifurcation point between cyclical dynamics and chaos. And what happens here is that we see periods where there are more regular dynamics that can occur, that can shadow almost a cycle. And then we have periods of bursting, of more turbulence, of breakdown of these localized patterns. You have recurrent patterns here that then break down to more turbulent and then recover another type of cyclical, almost cyclical like pattern. And if you look at the power spectrum, you see here a mixture of this one, which is a noisy spectrum, and a few spikes that mark the proximity of a periodic component. So what is the edge of chaos? The edge of chaos intermixes regular components that are near cycles, near cyclical components, and chaotic components, and it occurs also at the onset of chaos. So the concept of edge of chaos can be expanded to deal as well with chaotic dynamical systems, even with dynamical systems with only one variable. At the onset of chaos, we have precisely the main point of the definition of the edge of chaos, which is the intermixture of regular quasi-cyclical structures intermixed with randomness. And we see here in the power spectrum that precisely, which is a mixture of this one and this one. Okay, so at the edge of looking at the mean field, at the mean value of each row of these oscillators, we also see here the edge of chaos as well. In the bursts of activities, we see it in this power spectrum, in these rises in the power spectrum. So precisely the edge of chaos in a coupled nonlinear map, which is a spatially extended system, we see these rises in the spectrum correspond precisely to allow us to identify the pattern of the edge of chaos. And the edge of chaos does not necessarily imply that there is a power law decay in a power spectrum, which characterizes self-organized criticality, a concept that we'll see soon enough. But in this case, it occurs a slight power law drop in the power spectrum, and this rises. But basically, what characterizes the edge of chaos is the intermixture of noise-like dynamics and a few spikes that characterize, or a few rises in the spectrum that characterize proximity, or a resilience of a cyclical skeleton. So an intermixture of order and randomness, of periodic or quasi-periodic order and randomness. If we go more to the chaotic side, to the chaotic region, those spikes are less pronounced. You still have a rise in the power spectrum here, but it's more, we don't have those more regular identified structures. Here we are dealing more with the so-called class 3 dynamics that Wolfram identified in the cellular automata. So here we are dealing with the more random pattern and not as ordered, or not with such a pronounced presence of a strongly resilient cyclical structure here. So what is the edge of chaos then? It's a transitional regime between a random dynamics and a regular, cyclical, or quasi-periodic dynamics. It's very important because many systems exhibit it. In cellular automata and networks of chaotic oscillators, it can be identified in the phenomenon called spatiotemporal intermittency, which you're seeing on the right. An important point here is that we'll see that it occurs in COVID-19, the edge of chaos. In nonlinear dynamics of nonlinear dynamical systems, even low-dimensional systems, it occurs in a dynamics near a bifurcation point at the onset of chaos. It can be characterized by weak chaos, that is chaos where the butterfly effect takes a long time to take hold, which means that you can get some predictability, a longer term predictability. Uh, and this weak chaos can be either low or high dimensional. The high dimensional corresponds to the concept of homeochaos introduced by Kuhiniko Kaneko, so the, the the Japanese author that addressed strongly coupled chaos, which was the main author in coupled nonlinear dynamics. So chaos in networks. The presence of persistent periodic or quasi-periodic signatures can occur, and in stochastic chaos, it can be induced by the coupling to a noise field. This is the phenomenon known as noise-induced order. So, homeochaos is one example that was introduced by that was addressed by Kaneko and Ikegami, and corresponds to chaotic dynamics with low values of the largest Lyapunov exponent, which characterizes the strength of the butterfly effect, and leading to a self-organization towards a weakly chaotic dynamics. In the initial proposal, homeochaos is high-dimensional, that is, it is characterized by a large number of degrees of freedom. However, the possibility of homeostatic equilibrium associated with emergent low-dimensional weakly chaotic dynamics is also possible, which leads to low-dimensional homeochaos as a variant of homeochaos, and this appears as we will see in the SARS-CoV-2's epidemiological dynamics. The edge of chaos, and the basic issue regarding homeochaos and the edge of chaos in general is regards the dynamical stability of attractors. We have, in the case of homeochaos, we have the dynamical stability of attractors, weak chaos, and low or high dimensionality corresponding to, depending on the corresponding attractors. So, but the major issue around all this, which is raised by by Michael Crichton in the second book about the edge of chaos. And the early works on the edge of chaos noticed that complex adaptive systems maximize their fitness if they were self-organized, they co-evolved towards the edge of chaos, which made the edge of chaos an idea that that complex adaptive systems could show an optimizing behavior and stabilize at that razor's edge, near that bifurcation point, intermixing regular structures and random-like dynamics. But the problem is that this realization led to an assumption that of the possibility, led to a conjectural standpoint that life might self-organize towards the edge of chaos, and or complex adaptive systems might self-organize towards the edge of chaos, and then and then stay there, and the edge of chaos would become like the great attractor for complexity. The issue here is that is raised in Michael Crichton's book at a time where the edge of chaos was being considered precisely as an important attractor for complex structures to emerge. Complex structures in the sense that they would intermix a certain randomness and the necessary innovation and the necessary novelty, but also conserve the necessary regularity to survive. And the issue of complexity, and especially in the Santa Fe Institute, they started to think about complexity not in terms of randomness or style, white noise style randomness, where no pattern would emerge, but they started to think and reflecting considerably what was addressed already by Ilya Prigozhin in the dissipative structures concept, and also by Haken, which is the possibility, which is that complexity arises by intermixing what seem to be random-like patterns, but also complex conserved structures that are either periodic or quasi-periodic structures. So this structuring was considered leading to the so-called edge of chaos. And the echoing those other elements as well, the Santa Fe Institute started to think, and people started to think within the complexity community that the edge of chaos might be one of the co-evolution towards the edge of chaos would be the great attractor. The problem is that is it stable, the edge of chaos? In the case of Prigogine actually in La Nouvelle Alliance, which was a book that he wrote with Isabelle Stenger, he tended to consider an instability at a critical point of phase transition between phases that would lead to bifurcation. So the possibility was that Prigogine opened up actually in that book that what he characterized a situation similar to the edge of chaos, but he considered it as difficult to maintain that position, difficult to remain at the edge without a bifurcation occurring. So without a significant qualitative change in the dynamics. So the Santa Fe Institute tended to consider the coevolution towards the edge of chaos as robust. The issue, however, is whether the edge of chaos is robust in coevolutionary dynamics, which is the main point raised in the Lost World book. Is a major point, and while in some toy models it can be robust, in nature the robustness is not necessarily guaranteed, and we'll be seeing that in the case of SARS-CoV-2. There are several problems related to non-fixed dimensionality in open networks and sudden structural changes in emergent attractors that can occur and that can be addressed even in the synergetics paradigmatic basis. That open up the possibility of the edge of chaos not being as robust as one may think. So the first challenge is that to the edge of chaos is that the emergence of finite dimensional chaotic attractors affected by noise in the collective dynamics of large open systems, finite dimensional attractors that may be near that bifurcation point, okay, so often tend to lead to those edge of chaos signatures. At least that's what I found out in different systems. In different systems where I found markers of edge of chaos, they usually had markers of chaos. So they were chaotic attractors near the onset of chaos. And they had that spectral signatures that intermix quasi-periodic structures and chaos. And we'll be seeing that in the COVID-19. So we can have that edge of chaos occurring in this case corresponding to an example of the concept of onset of chaos in complex systems. But the problem is that emergent attractors or even the self-organization towards the edge of chaos structural changes in the dynamics can occur. One of the possibilities is the change in the dimensionality of the collective dynamics. And this is a point that was raised by Kaneko and Tsuda in this quote. It's an important factor in the evolution dynamics is the change in the number of degrees of freedom themselves. So when a new species, for instance, appears, its population must be included as a new variable. Thus, the number of variables can change in time, and in conjunction with those cases of chaos where the number of degrees of freedom can change, the concept of open chaos was proposed. So they proposed another concept of open chaos, which is chaos where the number of degrees of freedom change. But even if an emergent attractor with a specific number of degrees of freedom emerge, and even if we get in dynamics near the onset of chaos, a change in the dimensionality can occur from a change in the number of degrees of freedom, for instance, or a structural change, and the patterns that we usually associate with the edge of chaos can be placed into question. The same holds in general for the edge of chaos. So here it's important to recover synergetics. In a large system, coevolution can lead to emergent collective dynamics, This is possible. In this case, the collective macroscopic degrees of freedom correspond to what are called, in the synergetics terminology, ordered parameters, and they span a finite dimensional geometric space associated with the system's dynamics. And with the microscopic fast dynamics sustaining this high-level dynamics in the form of a feedback loop that effectively locks in the lower level dynamics in the sustainability of that higher level dynamics. So we have the system being characterized by specific geometry. The system's dynamics can, in this case, be described by the higher level dynamics, which can have a fixed number of degrees of freedom, is emergent and is sustained as an emergent geometric order with a fixed number of dimensions. So we have a specific dimensionality, a specific geometry, and a specific topology characterizing the system. A challenge to this and edge of chaos markers can occur as a consequence of this. A challenge to this dynamics can come from feedback from the lower level dynamics that can lead to changes at the higher level, to the point that the level structure itself can change in time. Either the level structure is and this level structure can be changed chaotically. And in networks of chaotic oscillators, this can happen and was addressed by Kaneko and Tsuda in their book Complex Systems, Chaos and Beyond. And in extremis, the dimensionality may fluctuate in such a way that no fixed macroscopic geometry can emerge. This is one possibility. But in many systems where self-organization and even near the onset of chaos occurs, that is near a bifurcation point between a cyclical trajectory or a quasi-periodic trajectory and chaos. When we have that, and have signatures of the intermixing that randomness and those periodic structures, we can have this. But the issue is the stability of this dynamics and we will see that it's not as stable as we thought, and we'll see an empirical example of that in regards to the SARS-CoV-2, so the COVID-19. So the issue of of the emergence of a chaotic attractor or a high-level macroscopic dynamics corresponds to the so-called slaving principle in synergetics. The slaving principle is actually a concept introduced by Haken. It's basically a methodology. It supports a methodology by which when that applies to a specific situation, and the situation is the one described here. Basically, we have an emergent specific geometry with emergent macro level variables that characterize the system, that these dynamical variables that are at the macroscopic level effectively there's a feedback loop that lock in the lower level fast dynamics, macroscopic level dynamics that comes to work for the sustainability of that macro level order. That is characterized by specific geometry, by specific topology in dynamical terms. If we represent those order parameters in a geometric space, their dynamics in a geometric space, we can get an attractor, including a chaotic attractor. So chaos is an example of emergence of chaotic attractors in complex systems, is an example of this dynamics that is addressed by Aken. With this, and the systems dynamics can be characterized by understood and characterized by looking at that macro level dynamics, and this is the so-called slaving principle. However, the issue is that chaos and synergetics led to a specific finding regarding chaos, and the finding is that while one could the chaotic attractor is an example of this emergence of macroscopic variables of in a complex system with many parts in interaction, with many degrees of freedom, possibly even open in terms of entering and exiting new elements. We can have all this and still a robust structure emerge. But then if we try to reduce the number of variables, and we can approach the system in terms of those few number of variables, but then if we try to apply the same analysis and reduce and describe those variables in terms of a smaller number of variables, we find that we cannot. And this is an interesting issue, because what Haken concluded when looking at chaos is that precisely at the Lorentz attractor that we saw previously, Haken discovered that those degrees of freedom could not be reduced when one was at the chaotic regime. So the dimensionality is structurally irreducible. So the emergence of stable chaotic attractors in complex systems, this is an implication of Haken's work in synergetics, and it's a very important implication regarding chaos. One is that there is whenever stable chaotic attractors emerge, there is an emergence of a few ordered parameters that are effectively sustained by the system's dynamics. We are placed before that situation. But the second implication is that there is a limit to the adiabatic reduction method of analysis, that is the application of the Haken-Slavin principle. Namely, the order parameters are irreducible with respect to the methods applied by synergetics, leading to a failure in the Slavin principle's methodological application to the emergent active degrees of freedom associated with the chaotic attractor itself. So the dimensionality of the dynamics geometry is irreducible. This is a very important point. Why slaving principle? Why the term slaving? Because Haken says that the lower level dynamics is effectively slaved. That is, it starts to work for the sustainability of that specific order, and is not free to. It's no longer there is no longer. For instance, it's not free to work for another order that is not that one. So it's locked in. That's the idea. It's locked in to work for the sustainability of that specific geometry. And that geometry is robust. Of course, there can occur instabilities. And when whenever such a self-organization happens, as described by Haken, whenever there is an emergent attractor, we have this lock-in, and the slaving principle applies. But the issue of chaos is that we cannot apply this. There is no further emergence from that chaotic attractor of an even lower number of variables. That geometry is irreducible. So it structurally characterizes the system. The problem is then what happens when we have a bifurcation? We can have a bifurcation with the same number of ordered parameters and the same dynamical rule. We can have that emergent dynamical rule, but we can also have a change in dimensionality. And if you have a change in dimensionality, or you can also have a change in the dynamical rule without a change in dimensionality. But whenever that happens, there was a structural change in the system. So this can happen, which raises the issue that also with regards to synergetics, applying synergetic standpoint, we can have a self-organization, yes, towards the edge of chaos, but it does not mean that it stays there. Structural changes can happen, and if those structural changes happen, the attractor can change, and we have a different dynamics. The emergence of stable chaotic attractors in complex systems, this is very important. The geometry, the dimensionality of the dynamics geometry is irreducible. It's a proper of that dynamics. And the synergetics leads to a major point regards chaos, regarding systems dynamics and chaos. Chaos leads to an irreducible dimensional order in the system's dynamics, in adiabatically irreducible in Haken's sense, and changes in the attractor dimensionality occur as a structural change in that dimensional order. So emergent attractors associated with diverse open networks of interacting systems with fluctuating degrees of system falls well into the operative conceptual domain of the synergetic school, and any type of macroscopic order can occur. Chaotic attractors can characterize the system's dynamic. Edge of chaos-like signatures can also occur. It depends on the system in question. So changes in macroscopic dynamics means that systemically the conditions of sustainability have changed. So the micro level, which was working for that specific, was locked in and working for that specific geometry with that specific dimensionality, changed. And whenever structural changes happen, and those changes can occur in the emergent attractors topogeometric structure, that is topological structure, geometric properties, and so on, and also in the attractors dimensionality. And in coevolutionary context, such changes can be related to the system's survival. However, in competition or risk settings in interacting systems, a sustainability problem leading to a change in macroscopic dynamics can favor one system but be disruptive for another. And we'll see that in regards to COVID-19. So considering then the epidemiological problem, for instance, a virus contagion dynamics among human populations depends upon biological factors, including virus characteristics, incubation period, first time the systems can appear, the type of symptoms, the number of asymptomatic cases, morbidity, mortality, the mutation rates for the emergence of new variants, as well as the infected population and transmission vectors. On the other hand, there are also other factors that include a country's population, behavior, genetics also, and the measures put in place for healthcare response, quarantine, treatment, drugs, vaccination policies, and even healthcare communication and public education on the virus and the healthcare risks associated with it. All this enters into play. And all this, including the rate at which new variants surface, enter into play. And this quote is from one of my early articles on SARS-CoV-2, which found low-dimensional emergent chaotic attractors with markers of the onset of chaos in the regional epidemiological data for SARS-CoV-2. So here, the issue, the coevolutionary issue is very important because the way we as human societies respond to viruses and associated diseases with adaptive measures will that feedback will affect the epidemiological dynamics itself. So there is this complex adaptive dynamics of human societies in response to virus contagion and outbreaks, a response that in turn influences the viral propagation dynamics and the occurrence and pattern of outbreak waves, as well as the surfacing of new variants, depending also on the mutation rates, with possible complex attractors emerging from this situation. We have here a strong coevolutionary dynamics. And in the case of the virus, the pressure is for the virus to propagate. So we have here a race, an arms race, a biological arms race, which is the concept used in evolutionary biology, where the virus pressure is for the virus to propagate through the population, to become, even to override or overpass the immune responses. And on the case of the human population, we have this this attempt to control the virus, both in their bodies in terms of the formation of antibodies, but also in the case of human societies with the putting in place of healthcare measures, political measures, so on, to contain the virus, to respond to the healthcare crisis involved. And this is the coevolutionary problem. This includes also the reading of statistics. For instance, if you have this time series of the number of new cases for the virus, this can be used of new identified cases, of new deaths, new hospitalizations, and so on. These statistical variables can be used to to adapt to the virus. So by human healthcare authorities for policy making, for viral outbreak containment strategies, and so on. So the issue is then this same series, but these responses will affect those series because, for instance, if we go on the virus, we have now a large outbreak, and we had lockdowns. Then effectively we can curb that outbreak, and the lockdowns will lead to a decrease in the contagion dynamics, in the contagion speed, and we have less new cases after a while. So our response affected our reading. There's this feedback. Our reading of the time series affects the future dynamics, and the time series will change in accordance to that because of this co-evolutionary race. And here we have for different continents. This was from the 2022 article, from my 2022 article, which was published in the International Journal of Swarm Intelligence and Evolutionary Computation, which identified low-dimensional chaotic attractors in SARS-CoV-2's regional epidemiological data. It was also published in medRxiv as in the pre-publishing. So we have here Africa, and in case of Africa, this is 2020. This was 2022. In the case of Africa, we saw here a multiple wave pattern, but in the case of Asia, we saw and Europe, we saw these large outbreak waves. We'll see that this is a characteristic of the virus, which is called a rogue wave pattern. In the case, while in the case of Oceania, however, we seem to have this almost flat zone and then a turbulent zone. Actually, in the case of Oceania, there was a change in the attractor, precisely what we were talking about earlier. And we'll be seeing that shortly. And we'll be seeing what it was linked to. So basically, the analysis identified that all the attractors were three-dimensional. We had chaotic attractors with largest Lyapunov exponent that is small, 0.002, 0.002, 0.002, 0.002, and near 0.002 here also in South America. So these are low largest Lyapunov exponents. Typically, they occur near the onset of chaos. And the dimensionality of these attractors was identified as three-dimensional attractors. In the case of this is in the case of the new cases per million. So we have underlying attractors responsible for that dynamics. In the case of the number of deaths, we get different dimensions: 5, 3, 4, 5, 4. Some differences in terms of dimensions, but for the new cases per million, we got the same dimension for all the attractors. And if we look at the power spectrum, we see here a power law decay in the spectrum, and also here a spike for Africa. For both the new cases per million and the new deaths per million. And as we saw, these spikes mean that there is a close proximity to a cycle. It signalizes the possibility of the onset of chaos. In the case of Asia, we also have this spike, less so. But in the case of the new deaths, we see here more or less first a power law decay, but then a white noise spectrum there. So you don't get that pronounced cycle. In the case of North America, we see the multiple cycles here. So multiple cyclical signatures, which indicate a strong quasi-periodic or periodic skeleton present here, which is characteristic with the low dimension, with the low level of the largest Lyapunov exponents, indicates a system near a dynamics near the edge of chaos, near the onset of chaos. So edge of chaos dynamics, a mixture of randomness, but also the presence of cyclical structures here. So near cycles that are resilient when an attractor is near the onset of chaos. And look, this is a complex system as we described. We have here an example, a perfect example of Haken synergetics working. So we have the emergence of a chaotic attractor, a low-dimensional chaotic attractor near the onset of chaos. So here again, the spikes in South America, and so in North America. Okay. So for different regions, we see markers of a dynamics near the onset of chaos, and we see typical edge of chaos markers in terms of dynamics. The issue here is, and this dynamics actually is very predictable for the so for an artificial intelligence, an adaptive artificial intelligence using the topological structure of the tractor is capable of predicting the dynamics with more than 80%, and in the case of North America with 77% predictability. That's a little bit high as well, except for North America, which was slightly lower. And in 30 days ahead, we also had so a month ahead prediction, we can predict the series with large R-square scores. So this high predictability, more than 80% predictability, for instance, for Africa, for Asia, and so on, this is typical of dynamics near of an edge of chaos like dynamics, because there is a low, the largest Lyapunov exponent mean that the time for the butterfly effect to take hold is longer. So we have a larger foresight time, and we can predict the series more in the long run. And the fact that there are resilient cycles in the structure, despite the chaos, there are these the ghosts of the cycles are there, or of the quasi-periodic dynamics are there, and this regular dynamics that integrates the edge of chaos makes the system the dynamics more predictable, which means that AI systems can be used to predict the epidemiological dynamics a few days ahead, and used even a month ahead, and be used by healthcare authorities. The article was quoted and divulged internationally, actually, and this issue, and you have here and this issue can be this approach can also be applied to the Wilbissing Oceania case, which I talked about earlier. This was just these results are just for now just being shown for the countries, for the regions where where an emergent stable attractor was found, a stable chaotic attractor. And in the case, not only we can apply it to that, to the number of new cases, the number of new deaths, but here we also have for the daily hospital occupancy from COVID-19 in the USA and Canada. In the case of the USA, we have a 9-dimensional attractor nearer the onset of chaos with a lower Lyapunov, largest Lyapunov exponent. In the case of Canada, actually the attractor is lower dimensional, but the Lyapunov exponent, largest Lyapunov exponent, is slightly higher. And it's strongly predictable. We can predict 45 days ahead with 96% precision for USA and 95% for Canada in the coefficient of using an adaptive topological AI system that was used in this article as well. The issue also here we have onset of chaos like dynamics. But the main issue is that when I saw this, the fact that they are near the onset of chaos with these resilient cycles, on one hand, there is the good news that we can predict it on the longer run. The bad news is that the issue of stability of the dynamics at the onset of chaos is raised. That is the possibility of bifurcations occurring, either through the emergence of new variants or through changes in the healthcare response, and both. So, and we see that in the Oceania case. So in the Oceania case, we saw a bifurcation. Before there are actually there are two periods. This period, which characterize up to 2022, near 2022. 2021, yes, up to 2021, we had 2021, we had one dynamics in Oceania, And this dynamics is mainly characterized by Australia's dynamics, where you have a strong containment of the virus. Because they had strict rules in viral containment and were able to significantly contain the virus. But then in 2021, when then the measures were somewhat were relaxed, vaccination was put in place and so on, and then we had the surfacing of the Omicron variant, Delta and Omicron variant, and this led to an instability in the attractor. And basically, we see here an example where the dynamics at the edge of chaos is not stable. We have here one dynamics before, which shows the turbulence and the same markers that we saw here in the others, but with low numbers. Then the attractor loses stability here between 2021 in the first in the months of 2021. I see here the loss of stability in the attractor with a rise in cases. Here the maximum was 30 cases per million, and then we have 175. But then and then this is when the attractor lost stability, and then we had a new attractor, which is more turbulent, and you have the spikes in deaths and the rise in new cases. And these rise in new cases were up to 4,000 per million. It's the new number of new cases per million. So, and here we have actually the power spectra do not show that those a significantly higher spike. It shows a smaller spike here, but there's a spike here. Then the with a stronger power loss scaling here, a flat, an almost flat spectrum, fast convergence to a flat spectrum in the bifurcation stage, and then a return to a power law decay here on in the power spectrum with a spike there. So, and the problem here is that we see this the change, a bifurcation in the dynamics in SARS-CoV-2, linked strongly to the surfacing of new variants. And this is a basic instability in the case of SARS-CoV-2. SARS-CoV-2 leads to edge of chaos-like signatures, yes. Emergent low-dimensional attractors. However, it can bifurcations can occur, and the attractor can lose stability, and this can occur with the surfacing of new variants that can overpass the immune responses and lead to new infectious cases and rise in infections. And we are not on the clear in regards to SARS-CoV-2 yet, in regards to that, because the virus became endemic, and this is a problem. So the near edge of chaos dynamics, this co-evolutionary dynamics for the edge of chaos-like dynamics in the case of SARS-CoV-2 places a problem in terms of the possibility of instability at the edge of chaos, which is the main point of this this whole one of the major points of this whole presentation. So basically, this was one of the issues. My main conclusion in this article, which was from 2022, was that from the results obtained from the analysis, we find that we do not have an homogeneous attractor for all the regions. Different regions show key differences because I applied topological data analysis. And in terms of attractors and predictability, despite having the same dimensionality in the case of the new cases per million. For instance, North and South America do not exhibit black noise-like spectra, which is persistent noise, in the new cases per million, while for the new deaths per million, North America is the only one that does not exhibit a power law decay in the spectrum. The attractor's dimensionality is the same for the new cases per million, but not for the new deaths per million. And in the case of the persistent homology dynamics, which was one of the topological data analysis methods that will not be revising here, just want to the main conclusions. We found a division in two main groups, Asia and Africa on one side, and Europe, North and South America on another side. So the evidence is favorable to the hypothesis that the attractors are near the onset of chaos and reinforces the possibility of bifurcation, since from the Oceania case, we know that bifurcations can happen and that they are linked to the emergence of new variants. So this is a qualitative analysis. So from a time series of data, applying chaotic attractor reconstruction, which specifies a specific dimension, tries to find an optimal dimension and time lag for embedding a time series, we can find an underlying attractor. So this is more or less what Ian Malcolm, what Michael Crichton, um, uh, uh, placed Ian Malcolm doing. So Ian Malcolm analyzed the park's data and address the dynamics in the phase space dynamics. So he had to reconstruct the dynamical attractor for this park. So that's the idea. And the qualitative analysis, topological analysis of the attractor allows one and that an interpretation of the topological data analysis of the attractor can lead and of other nonlinear time series analysis methods in empirical chaos theory methods. Coupled with systemic analysis, allows one to interpretatively find insights on the system's dynamics and on the in this case, allowing one to make a prediction in terms of risk analysis. And the prediction here is that there is here an instability, the possibility of bifurcations could occur. And they did occur in the case of Oceania. And we can track down through systemic analysis. In this case, historical analysis was applied. I analyzed what happened during that period in Oceania and why did those cases arise? Why did the bifurcation occur? How? I analyzed what the healthcare authorities were saying that during that period, what the main media were saying, and I identified that they were having a problem with the Delta virus and the Omicron virus and the Omicron variant. So the Delta and the Omicron variant were at fault, strongly at fault for that bifurcation. So they are linked, and this is the conclusion from that systemic analysis, that they are linked to the emergence of new variants. And this evidence implies that we do not have a dynamical self-organization to a long-term stable equilibrium associated with the endemic virus. This was the second conclusion, that has reached a stable infection profile. In this way, healthcare authorities will need to be attentive to new variants and possible containment measures, as well as adjustment in vaccination policies and drug discovery for dealing with these new variants. This was the main issue. So, and this was for, and there was another article that quoted this, that actually quoted this article that I published. This article was published by other authors that also identified this is a quote from that other article, and they identified also chaos markers in COVID-19 data, but they identified markers of periodic and quasi-periodic subseries. Now, this is the perfect definition of the edge of chaos. So we are typically in this pandemic, we have characterization of edge of chaos. So the finding of periodic or quasi-periodic subseries were expected because the system was near that onset of chaos, and edge of chaos-like signatures occur. So in terms of spectral analysis and in terms of systems dynamics analysis. So this is the first issue, the edge and instability on the edge of chaos. The second issue that we have is in the case of COVID-19 is the so-called Malcolm effect that was also proposed by Michael Crichton in Jurassic Park. What is a Malcolm effect? But basically, the Malcolm effect is a situation. It was named after the mathematician Ian Malcolm, so the chaotician and complexity scientist that Michael Crichton invented in book, and that was portrayed by Jeff Goldblum in the movie series, as stated. And there was the concept of Malcolm effect, he called in which there was a speeding up dynamics, and a large disruption could occur, or these systems had an inherent instability. And Malcolm effects can occur actually, and I studied them actually in my PhD thesis and found them and analyzed them first in an article with my mother, Pedro Gonçalves, in the 2009 article. Malcolm effects may take place in a chaotic system with systemic risk, where deviation in the chaotic behavior may occur towards a more volatile period, characterized by extreme variations relative to the system's natural fluctuation interval. So these are Malcolm effects. They occur in the Rosler attractor. This is an example where we have that speeding up and the surfacing of these large waves. These correspond, in the case of hydrodynamics, to the so-called rogue waves, are close to what in the hydrodynamics are called the rogue wave dynamics, which are also addressed by chaos theory. And this is an example of another attractor, chaotic attractor. And the rogue wave phenomenon is seen here in this large region, that in this rise. It can also occur in stochastic chaos, and here is the noiseless version. Here is with noise, and we see here that we have periods where almost no fluctuations seem to be taking place. They are actually taking place, but then we have these high rises that dwarf the lower level fluctuations. These are examples of Malcolm effects. Here we have it in the SARS-CoV-2. In this case, this is my last article, which was published in 2024 for China, in the analysis of China's COVID-19 new number of cases, confirmed cases of COVID-19. And we have here the rogue wave phenomenon. We have here the Malcolm effect occurring. And what seemed to be here, like we have here a large wave of infections, which was linked to outbreaks in large cities and surfacing of new variants as well. We have here the problem. What seems here as a flat line is actually not a flat line. We have smaller rogue waves here, and these smaller rises, exponential rises, and fall and drops. And if you look at these almost flat lines, we find other rises and so on. This is an example of self-organized criticality. Actually, we found evidence of self-organized criticality here. And self-organized criticality was proposed as an explanation of power law decay in power spectra of complex systems dynamics. We saw a few examples of that already. And it grew as a theory within the complexity research field to address the emergence of power law temporal on-door spatial correlations, leading to scaling variance, that is fractal laws, in time and or in space as a result of complex system self-organization. So it's the idea that systems can self-organize in a critical phase transition, like a transition between solid and liquid or liquid and gas, for instance. While it may be confused with the edge of chaos, it's not the same. And SOC can occur. The occurrence of SOC does not mean that we have a system near the edge of chaos. These are different, they can occur in different contexts, and no, they are not exactly the same. So the initial proposal of self-organized criticality addressed specifically fractal scaling signatures, but we also have these multi-fractal dynamics that can occur, and the theory addresses bottom-up rather than the top-down occurrence of fractal laws in systems dynamics. In the case of the epidemiological rogue waves, we do have this power law decay in the power spectrum, but we also have multi-fractal signatures, which characterize typically, we do not have a single fractal law, we have different fractal laws in the signal. And this characterizes typical turbulence processes. The main conclusion in the article was that this was chaos-induced self-organized criticality, in this case of the multifractal kind of self-organized criticality. And we found that an adaptive topological agent was able to find that the highest prediction was obtained for a three-dimensional attractor. So the three-dimensional attractor was the dominant attractor for the new cases of COVID, new identified cases of COVID-19, which matches well the data that we have for the different regions for 2022. But in this case, for a single country, which is China. We have here the predictions using the attractor. We can predict the series, as we said, using even without knowing the equations, but using an artificial intelligence, an adaptive topological, an adaptive artificial intelligence with the topological machine learning. It can predict the series very well, 87.567% of R-squared score, a correlation between the agent's predictions and the series, even without knowing the equations for the dynamics, just reconstructing the attractor, we can predict the series. And this is what Ian Malcolm would be able to perform given data, given a time series of data. One of the conclusions, but what's interesting here is what are the main qualitative conclusions of this in terms of systemic analysis. First, the attractor is chaotic. We have a chaotic attractor, but it's not as close to the edge as the other attractors that we saw for the regions in the 2022 data. The largest Lyapunov exponent is approximately 0.0322, which gives a Lyapunov time. If we invert the largest Lyapunov exponent, we get an estimation of the prediction of the time it takes for the butterfly effect to take hold, the uncertainty to take hold. And we have here between 31 and 32 days, which coincides with the time it takes, which coincides with using the topological adaptive AI system and trying to predict several days ahead. The first time that prediction performance of the agent drops below 50% is between 31 and 32 days, which matches exactly the Lyapunov time. Now, if we represent the attractor, the reconstructed attractor in three-dimensional space, like the Hostler attractor, where we had that region of escape, that region of rise linked to rogue wave phenomenon and to the Malcolm effect, that accelerating effect. We find that looking at the attractor structure, we have here a three-winged attractor. These three wings correspond to are responsible are structure for correspond to the structure in the attractor that explain that acceleration and rise in terms of rogue wave dynamics. So the epidemiological rogue waves can be seen in the topological, in the geometric structure of the attractor linked to this three-winged escaped structure. And the three-dimensional attractor with this three-winged structure exhibits the Malcolm effect precisely because of this of these rises. So the three-winged attractor, the Malcolm effect, is linked to, in the COVID-19 dynamics, to the rogue wave pattern, which in turn is linked, in the case of China, to a multifractal turbulent pattern associated with the propagation of the virus. The Malcolm effect is explained geometrically by an underlying chaotic attractor with a three-winged structure, an emergent chaotic attractor, which explains rapid exponential acceleration. And the attractor is a complex consequence of the virus characteristics, the surfacing of new variants that tend to accelerate fast, lead to this accelerating fast exponential rise of the virus, and also to an urban transmission. So the SARS-CoV-2, since it is not as close to the edge of chaos, in the case of China, the likelihood of bifurcation is lower, though not negligible. That is, the attractor is in a more robust stage of chaos. However, this means that the attractor is more robust, which means that future Malcolm effects are possible. That is, the rogue wave pattern is likely to continue as long as variants that overpass the immune system, as if a new variant occurs with rapid dispersion, that is able to lead to new infectious cases and to a rapid rogue wave phenomenon, we can have that. And it's important to notice that, for instance, in the case of Portugal, we are having a problem with COVID-19 right now. And this problem is underreported in terms of the actual number of cases because we do not, we are not recording exactly, and most countries are not doing that, the exact numbers of new cases of COVID-19. They are not being as reported and as controlled as during the pandemic period. So you can have hidden rogue waves that we do not know that they are happening, and but are happening, and we can have high number of deaths in the rising hospital cases that catches us by surprise because with numbers not as high as those that would be expected. And we think that, but actually the wave is much larger than we think. So SARS-CoV-2 is now endemic, and the rogue wave pattern seems to be its dominant pattern, actually. It is strongly linked to this coevolutionary process characterized by this biological arms race, which is also called the Red Queen race, with new variants surfacing for faster infection, which means that epidemiological rogue waves leading to added pressure for countries' emergency services, even with lower death rates, may lead to rising deaths. One of so the Malcolm effect and coevolution in the case of SARS-CoV-2, there are different possible scenarios: the slowing down or stabilization of mutation rates leading to a linear genome variant surfacing. This was one possibility. However, the most likely scenario is the exponential acceleration of new genomes is also another possibility, with diversity explosion that can lead to a worst case scenario. This is the worst case scenario. Uh, Perhaps the truth will be lie in the middle, but a possibility of a diversity explosion, we cannot rule out. This can lead to a worst case scenario of exponentially accelerating viral dispersion, a new pandemic phase with rising deaths. In this case, we need to study the evolutionary trajectory of SARS-CoV-2's genome shifts during widespread vaccination and the emergence of new variants. And in the case of Omicron variant, this was studied. So the main issue here in the case of Portugal is that we identified in this winter there occurred a great number of deaths. Some of them may have been produced by SARS-CoV-2, but may have gone underreported. Why? Because there were cases of simultaneous infection of SARS-CoV-2 and other virus, the respiratory virus, and the person may have died from another respiratory virus, but may have caught, for instance, SARS-CoV-2 first, fought the SARS-CoV-2, and then fought the second virus. So co-infection was identified here in Portugal and was reported here in Portugal, co-infection by two viruses. This is another problem regarding SARS-CoV-2. So, and this is an example of the application of chaos theory to empirical data, and not only, and we saw that not only we apply quantitative analysis, but also systemic analysis that allow us to get insights on systems dynamics. So chaos theory methodologically requires the following fields: nonlinear dynamics, topology, computer science and information theory, stochastic processes theory, network science, system science, statistical mechanics, field theory, systems philosophy. These are all areas that enter into current applications of chaos. And chaos theory, basically, as we saw, is about finding geometric order in the randomness to uncover, interpret, and understand that order. That is the main point of the theory. And in complex systems defined by a large number of non-linearly interacting elements, emergent strange chaotic attractors, fractal attractors, correspond to an emergent fractal geometric order, a dynamical form that is structurally sustained by the system's dynamics as a property of that dynamics that determines it. And when an attractor changes, the system underwent a structural change. That is one of the major insights. One can find the explanatory basis for understanding the system's dynamics from that attractor's geometry and topological properties. We could call it topogeometric. In this sense, to understand the system's dynamics, one needs to perform a systemic analysis of the attractor in order to better understand the systemic dynamical order. There is, however, a monster in chaos, which is algorithmic chaos, which was identified in generalized shift maps. This monster actually it means that it's a possibility, is a type of chaos that occurs where one is unable to apply. Undecidability occurs in regards to the major attempt at capturing the properties of the system. So, for instance, fractal scaling, multifractal scaling, there's a more complex structure than that. Any time, any scale in time or in resolution of the phase space, there is always qualitative behavior just around the corner that we did not identify. And no finite experiment is sufficient to guess the nature of the basins of attraction or of the set of periodic points that can be used for topological analysis. And this corresponds to the fact that these sets are recursively enumerable, but not recursive. And you can produce longer and longer lists of points or orbits, but no regularity will ever emerge that allows one to capture the entire set. So we are unable to capture the order here. This is of the level of mathematical undecidability. It's the incompleteness of mathematics that's raised here, which resents to Gödel's theorem. So this is the monster around the corner, and it was found in 1990 in an article, and it's available at the Santa Fe Institute. It was published by Christopher Moore, Generalized Shifts, Unpredictability, and Undecidability in Dynamical Systems. So this ends our presentation. The major articles will be placed on the video description. The major quoted articles in this in this in this presentation, and this ends effectively our this conference and the video series for the conference. So goodbye for those that are still alive at the end of this talk, and thank you for listening.